So in this video, I'm going to talk about the factors that affect solubility. Okay? Now remember that solubility is just the maximum amount of solute that will dissolve in a given quantity of solvent at a specific temperature. Now the specific temperature part is pretty important. Now and that is one of the factors that will affect solubility. Now the grams. Now we typically talk about solubility in terms of the grams of solute in the volume of solvent. Okay, this is how we talk about solubility. So most of the solutions that we work with are water, and they're specifically in the amount of solute that goes into water, 100 milliliters of water. Specifically, okay, and the pressure and the factors that we're going to talk about are temperature and pressure. Okay, so the first factor I'm going to focus on is the temperature. So like I said, the solubility will be affected depending on the temperature of the solvent. So what happens if we increase the temperature of that solvent? Well, this is a graph right here on the page that you can that is in your book as well. So on the y-axis over here, you see the solubility, and it's grams per 100 milliliters of water. Okay, so we are talking about mostly ionic compounds, but you also have glucose in here, in 100 milliliters of water. So if you start increasing the temperature of each of those solutions, what the heck happens to the solubility of each of those solutions? Well, good thing about ionic compounds is they usually will increase in solubility as you increase the temperature of your solution. Now this is because of the kinetic energy that you're putting into the solution that allows those molecules to be moving faster, right? And they'll be able to have more intermolecular attractions between the solute and the solvent, or the water, right? You also have glucose here, and this is the example that I used in a lecture where I was talking about increasing the temperature of my tea, and putting sugar in it will make it dissolve more readily versus taking cold tea and putting sugar into it. Okay? Now I also want to point out that not all ionic compounds will have a greater solubility as the temperature increases. One example of a compound that does not increase in solubility as you increase the temperature is the cerium sulfate down here. Okay, you can see here as it starts out at about 20 grams per 100 milliliters of water at 0 degrees C, but as you increase the temperature, it decreases its solubility, or it precipitates out of solution. And this is basically, and we'll go over this more later, but this is basically because of Le Chatelier's principle. This happens to be an exothermic reaction, so if you add heat to the overall reaction, it's going to drive the reaction towards the reactant side, which is the solid cerium sulfate. But most of these, it looks like all of these other ionic compounds here all increase in solubility as you increase the temperature. An interesting fact, NaCl is the one that we use most of the times, what we put on our food. It only barely increases in solubility as you increase the temperature, whereas all of these have a pretty drastic increase, right, as you increase the temperature. Not so much sodium chloride, okay? It does increase in solubility a little bit, but it stays pretty straightforward as you're going. Now you actually kind of saw this in lab when you went to go add your salt to your solution. It took a little bit, right, for you to actually see all of that salt dissolve. And that was because you were moving those molecules around. By literally stirring those molecules, moving those around, you were increasing the intermolecular attractions as you went. So you did actually add kinetic energy to the solution. Although you didn't necessarily increase the temperature, the fact that you were physically moving those molecules made the solubility increase slightly. Okay? Now all of these examples are all solids that are being put into water, right? But we don't just work with solids into water. We can also put gases into water as well. Now, the interesting thing when it comes to gases is the solubility will actually decrease for gases. Here, let me specify. The solubility for gases will actually decrease as the temperature increases. Now think about this on a molecular level. What the heck is happening? Well, it turns out that as that kinetic energy increases in your solution, right, those water molecules are moving faster and faster, they're essentially pushing out those generally non-polar gas molecules, right? There's not a strong interaction between the water and the gas molecules. So it's going to make those such that they're going to come out because those water molecules are going to be interacting more with an increase in that kinetic energy or an increase in the intermolecular attractions. Now the book actually has a really good example of this. When you take a glass of water and you get it out of the tap, if you leave it on your counter for a while and you start to see, and the glass of water starts to increase in temperature, you start to see bubbles lining the edge of your glass. That is the increase in temperature, and all of those dissolved gases are coming out and adhering to the glass. So that's one way that you've seen in real time how the increasing temperature of liquids, or a solution, makes the solubility of gases decrease. If you have ever fished before, you've also probably heard that you're not really supposed to fish at a hot time of the day because the fish are less likely to eat because there's less oxygen in the water. They're just a little bit less likely to eat if they aren't getting as much oxygen. Now, if we stick with gases for a little bit, we can actually move on to pressure and how pressure affects the solubility. Okay, so pressure doesn't really affect the solubility of liquids and solids so much because there's not a whole lot of room for the molecules to move around at that point. They're pretty well set in next to one another, right? But gases have this idea that they have this space in between all of the molecules where if you increase the pressure, you will actually increase the solubility of those molecules in the solution below it. So this is a diagram from your book where you have the flask, or the beaker on the right here, the left, has a lower concentration of gas molecules in the vapor phase above the solution. Now remember that pressure of a gas is just equated to the number of interactions of the gas molecules on the walls of the vessel, right? Or the surface of your solution here. Now on the right side, you see there is a greater number of gas molecules up above the solution, right? So you're going to have more interactions between the vessel wall and the gas molecules. So it turns out that we have a law that can actually describe this, and that is Henry's law here. So Henry's law just states that the concentration of the gas within the solution is going to be proportional to the pressure of the gas over the solution. Now, if this is a proportionality, right, we have this proportionality here, this bit right here. Now, how can we change that to an equality? Well, it turns out we can do that with a proportionality constant. And then we end up coming to C equals Kp, where the C is the concentration of the gas that is dissolved, right, and it is moles per liter. Okay, and pressure, it can be in millimeters of mercury, or it can be in atmospheres. As long as it stays consistent with the units of K, then it doesn't really matter what the units of the pressure are. Okay, and the pressure, or the Henry's law constant K depends on the gas solvent identities. Okay, so CO2 in water has its own proportionality constant versus you could also do, say, if you had H2 in water, that would also work. It just depends on the specific gas in a specific solvent, and those each have their own proportionality constant. Now let's take a look at equating this equation here to these diagrams again. Right, so if you increase the pressure, you increase the number of gas molecules that is above the solution, it's going to increase the number of molecules within the solution. Okay, and it will be that these gas molecules above the solution will be hitting the surface of the solution, and if there's enough of a drive to spread out, then those gas molecules will go into the solution there. And like I said, with K, it all depends on the identity of the gas and the solvent it's going into. So there are a couple of problems in your problem set for you to apply this Henry's law here, and we might go over some in class today as well, but I want you to practice using this so that you can see how the pressure of the gas above a solution will help or will change the concentration of the gas within that solution. It's pretty neat.